All right, thank you for the introduction, and hello GopherCon. So I'm actually here to prevent you from getting to lunch today, and to do that, I'm going to talk to you about preventing deadlocks and leaks in Go. So most of you have, I hope, or will sit down to make a big application in Go. And if you're going to do that, you should be using Communicating Sequential Processes, or CSP for short, because it's awesome. And now you're going to sit down, you're going to code up this really big application, you're going to pour your blood, sweat, and tears into it, or maybe just tears, or maybe just your colleagues' tears. And you're going to see a panic that starts with this at some point. And here's where the tears comes. Congratulations, Gophers, it's a deadlock. Or maybe you'll pull up the profiler, and you'll see something like this. Congratulations, Gophers, that's also a deadlock. Or maybe someone will come to you and say something like this. Hey, after 3 weeks, the Linux OOM killer jumps in and we have to restart stuff. That also might be a deadlock, or it could just be a leak. To borrow from Douglas Adams, don't panic. No matter how good the language is, you can still write bugs in it. So let's grab that towel and wipe away the tears. I've definitely been here. I've definitely written a lot of bugs. We now have over 5,000 instances of my first major Go application running, and it has a lot of long-lived and intercommunicating Go routines. And in getting there, on the journey to getting that deployed, my colleagues and I at Comcast Viper experienced these as well. So that's what this talk is about. The rules and the tips we developed to avoid these issues. But before we do that, for those of you who are unfamiliar, I'm going to take a step back and talk about communicating sequential processes. I mentioned it earlier. It's the concurrency paradigm baked into Go. In CSP, we communicate between processes by passing messages. This is the now classic share memory by communicating, don't communicate to share memory. These processes then execute sequentially. That is, we try to avoid concurrency in a process itself. Now, Go is a practical language, and we'll avoid that for, well, practical reasons sometimes. And now, before I tell you what a process is, I'm going to tell you what a process is not. And processes are not types. And for those of you from OO backgrounds, this isn't intuitive, but designing for CSP is not the same as designing for object-oriented. I mean, what would the type of a process be? A process is something fundamentally about inputs and outputs, a set of executed steps. Now, a type may run a process. The inputs and outputs of a process certainly have type, but a process itself is not a type. Hoare, the inventor of CSP, defines a process as the mathematical abstraction of the interactions between a system and its environment. The first thing Hoare tells us to do is throw out all of our preconceptions as to what a process is. The first process he describes is that of a vending machine, the insertion of a coin in the dispensing of chocolate, just in case you guys weren't hungry enough yet. That is the process the vending machine follows, not a description of the vending machine. The set of steps it executes, its inputs and outputs. We didn't mention any attributes about it. Now, CSP is about designing with process is, emphasis on the plural there. And to prevent deadlock, that's what we need to learn to do. And that's one of the single greatest features of Go. It's built to model not just a single process, but the interaction of many. It's built to model concurrency. And to help you do that, I'm going to talk through the design tips for CSP that helped us. These should help you avoid deadlocks and maybe simplify your code. These tips are collected from our own experiences at Comcast, some wonderful Go blogs and presentations, and of course the original CSP paper by Hoare. So when we're designing with CSP, we're going to focus on our data flow. We're going to draw out our communication, we're going to make pipelines out of stuff, and we're going to remember our exit strategies. So first and foremost, when designing processes, you want to focus on the flow of data, not the flow of control. Again, that's inputs and outputs, the movement of data through your system. what goes on your channels, what puts data there, and what consumes from them. That's why Go tells you to expose channels. Back to that vending machine. In comes $1, out comes some chocolate. Input and output. And this is something fundamental to designing with CSP. A process may have a decision tree, but the communication between processes is inherently point-to-point. Now, control flow has its place in a single process. This is where you ask questions like, where does this go? Your if, then, else, and other classic control flow statements belong to a process. What you don't want to do is look at control flow on the multi-process level. Then you have to start asking questions like, who's in charge? Rich Hickey, the inventor of closure, calls that place-oriented computing, and he has some great descriptions of its downsides if you want to look up the video. But it's also fundamentally not CSP. CSP is about communication of data, not ownership. Signals generally fall into this category as well, and I'll get back to that in a moment. When you design processes with control flow, you end up with something that looks like this. I like to call this a manager-driven workflow. Apologies to my bosses in the audience. To extend a Rob Pike analogy, you have some Gophers, and they're burning C++ books for heat. In this model, at each stage, some piece of control flow must take place, and it becomes very difficult to follow the sequence of events that is occurring. For example, to hand over a piece of work in such a scheme, a manager must be consulted, then the work's directed somewhere, and finally the manager tells the Gopher what to do with its work. And that's hard to follow, and that's hard to follow in code too. Now, a common sign of control flow is overdependence on signals. A signal is a message with no data. That's in Go, we use the empty struct for that. With signal channels, you haven't invoked a behavior on an object or called a function. You've possibly signaled something somewhere to do something. And consider this example. Our thread of execution simply jumps to another spot. We move from one function to the next, and you lose all context of what is occurring. And some of you probably are thinking that sounds a lot like Goto. Dijkstra, in the original Considered Harmful paper, said the unbridled use of the Goto statement has the immediate consequence that it becomes terribly hard to find a meaningful set of coordinates in which to describe the process progress. And I say that goes for signaling as well. And while we're at it, why don't we throw in callbacks too? This is in direct contrast to data flow. And this is really a fundamental concept of designing with CSP. What are the inputs? What are the outputs? And how are they connected? When we are talking about the composition of many processes, this should be our focus. The process of a vending machine communicates with you through its inputs and outputs. The connection of the two is what generates our multi-process system. With data flow, you have some processes. You've connected these inputs and the outputs together to form our overarching system. For software engineers, those inputs might be requirements in caffeine, and the output is code. For Gophers in this diagram, the input is the C++ books, and the output is, of course, heat. But this isn't just about dealing with shared state. It's also about decoupling our Gophers. They don't care who puts the books on their input pile, and they don't care who takes from it. They don't need to know any of the managers, and as a result, the set of instructions that a Gopher follows is simpler and less intertwined. It's more reusable, and that's something we really strive for in CS, right? And it's easier to follow in general. It reads well in code. Consider this snippet. We wait on input 1, and then 2, and then join them and place them on the output. You don't lose context on what is happening at each stage. Now, I challenge you to give a similar semantic using callbacks that's nearly as clean. This is going to fare a lot better in your code reviews, too. It's imminently understandable. So, now that we're talking about inputs and outputs, we need a way to describe the system. I generally find the best way to do this is the time-honored method of drawing. Plus, it's fun, and your whiteboards will look super complicated, and that's really the goal of any engineering task, right? Complicated whiteboards. Now, Hoare's original paper calls these drawings connection diagrams. A connection diagram really only consists of two things: a process represented by a box and an arrow representing directional communication. The arrow is from sender to receiver. In Go, the boxes are the Go routines, and the arrows are our channels. These drawings help us conceptualize the concurrent parts of our programs. And by focusing on inputs and outputs, we can begin to describe the processes themselves. This is a sort of Yoneda limit for processes. Now, in the spirit of fun, most of my connection diagrams will be using Go's Gophers as the processes instead. And you can grab these Gophers and add them to OmniGraffle or Visio. They're Creative Commons licensed, and the wonderful work of Renee French. So the other benefit of drawing is it lets us introspect some design decisions we've made. We can look for problems. A good set of these is God processes, rats' nests, and cycles. A God process is one very busy, hardworking Gopher. It may process a lot of distinct inputs and outputs. One sure sign of this is a heavily connected process with lots of different data types coming in and out. A process also may just be too busy, and that's when we can break it up to take advantage of multiple CPUs, hopefully. In this case, though, we may need to merge the results back together with another process. Now, a rat's nest occurs with a heavily interconnected set of processes. This is often because responsibility for an operation has been muddled between processes. This is also a fairly sure sign that some sort of control flow is occurring. And finally, we can look for cycles. Communication cycles in a drawing mean there's a potential for deadlock. We may want to remove the cycles or pay special attention to mitigating them. Which brings us to our next strategy, the kind of structures we want to create in our systems. And far and away the most important of these is pipelines. Now, a pipeline is a unidirectional flow of data. That's not just a single point-to-point flow. Data may fan in from many workers to a merger, or fan out from a receiver to many processors. It may compose the results of many disparate sources, say several databases, or may decompose a single mux stream into separate handlers for each incoming item. But generally, it should try to move forward. So instead of defining a pipeline as a unidirectional flow of data, we might also say it's a directed acyclic graph of processes. And this is really important because unidirectional flows of data cannot deadlock. And more things are pipelines than you think. Consider our classic publish-subscriber model. We have a publisher. It's got two inputs, subscription and unsubscription. And we have a subscriber for some set of events. An initial guess might produce something like this. We start our subscriber, we call subscribe, and when we're done, we unsubscribe. But that's not very pipeline-y, is it? We've got communication cycles in it. And this does contain a deadlock. If we unsubscribe as the publisher sends data to the subscriber, we have an issue. So let's make a pipeline out of this. If instead our subscriber hands some context, which was mentioned earlier, and I'll get more into depth, along with his subscription, he can cancel his subscription, and the publisher will not deadlock. When sending to the subscriber, we check if it's done, and if it's done, we delete it from our map of subscriptions, effectively transferring the previous connection diagram with its cycle to this connection diagram without a cycle. Our context is a new Go routine, which doesn't block either party. Now, the golang.org blog contains some fantastic examples of this, including parallel digestion of a tree represented as a pipeline. And our pub subpoint example just pointed out something very important. You've got to have an exit strategy. Many programs will be designed without this in mind, and then they'll introduce deadlocks when they add it. An explicit cancellation done with a signal channel, which is blocking, will suddenly introduce a deadlock on our previously fine program, the set of digesters and mergers. And exiting, in my experience, is the most common source of cycles in our diagrams. This is why the closed channel semantic was introduced, which is non-blocking. The other issue exiting brings us is leaks. If in this diagram, the exit signal is processed before the data from the sending gopher is processed, he'll be left hanging. The Go runtime cannot collect a Go routine until the function it's executing returns. So now you have a memory leak. And by far, the best way to exit is using Google's Net Context library. Peter mentioned that earlier. This is a fantastic library. With this library, you pass along a context. The context includes a done method that returns a channel. This channel will be closed when the context is canceled. This allows you to stop short an entire set of operations at once, and it's safe. You can cause done to cancel with a deadline, a timeout, or with a function call. One thing to remember with context is if you're using it, you need to avoid uncancelable operations. In any send, you must select against the context done channel as well. Context is also great for passing request scope values around, and the GoDoc and the blog on the subject is very good. That, of course, assumes you don't care about the results of an operation when a cancel occurs. But often we do, right? We're doing something and we hit a timeout, and we're going to collect all the results we got before the timeout. In that case, you need to follow this pattern. First, signal your children to exit. Next, collect all results. And finally, exit yourself. This means you need to keep a count of outstanding operations and make sure to receive all results before you exit. In this code snippet, we're farming out some work to multiple cores for fast Fourier transforms. When cancellation is done, all outstanding results are collected and sent before the function returns. If we did not collect the results in this case, we would have a memory leak. And you can see that's because I'm not selecting against the done context in that Go func. Now, when closing pipelines with context, we need to pay special attention to prevent leaks. We may not know the number of outstanding results, but we still want to collect them all. And in this case, each member must signal the next to exit, either by closing its channel or using a child context to exit when it completes. So let's run through a quick example here, really relevant to us at Comcast, and build an MPEGTS demuxer. Now, for those of you who are unfamiliar, MPEGTS is a video transport. We don't really need to get into the nitty-gritty on exactly everything it does. Also, for those of you who don't know, muxing is the process of joining separate pieces of data into a single stream. This is often done when your communication method is serial, for example, when you're bouncing TV signals off of satellites. To take these three pieces of data and mux them together, we first chop each piece of data into packets. Then we place the first packet of the first piece of data on the output. Then we place the second packet from the second piece of data on the output. And then we place the first packet of the third piece of data on the output. We repeat this for each packet. Of course, the rhythm of packets does not need to be repeated as it is here. Instead, we can place them on the packet on the wire with an envelope containing its destination. In MPEGTS, this is called the program identifier, or PID. So in TV, we often get several mux streams, say NBC, ABC, and CBS. We're going to lay out the processes necessary to demux these, not just the providers, but the audio and video for each. So let's start with our first rule. What are our inputs? Our mux streams on the left. What are our outputs? A demuxed audio and video stream for each provider on the right. Now we need something to receive the packets, and that pub sub example I mentioned earlier should seem like a good fit, so let's add that. Now MPEGTS, this is kind of getting complicated, contains a special data PID called the program assignment table. It rides on PID 0. And it tells us what streams are available in the mux, like ABC, CBS, and NBC. So we need to add a listener for that. Now, each program contains more MUX data, right? Audio and video. And that information is carried in something called the program map table. And the PIDs of the PMTs are listed in the PAT. And we use the PatListener to create a set of PMT listeners. So now we've got a PatListener that looks for our set of MUX streams, ABC, CBS, NBC, and a PMT listener for each stream that tells us about the set of content, audio and video. So the final stage is to add something to collate those packets we chopped up earlier back into something usable. We might get a single frame of video or a sample of audio, and I'm going to call these the depacketizer. And now we have a simple MPEGTS demuxer. However, the set of streams, ABC, CBS, may change. We may add a secondary audio stream. We may remove it. And so we need to add timeouts and components for detecting changes and all of that. And this is where it goes really powerful for us at Comcast, because these are very concurrent things. They happen in real time. So that's kind of what it would look like, given adding all this. And for those of you who are wondering what all those clocks are, MPEG streams have no less than 4 embedded actual clocks that run at wonderful frequencies like 27 megahertz and 90 kilohertz because of the vacuum tubes in the 1950s. And they use like 33-bit integers. So now some of you are probably thinking, well, that seems pretty simple. I have had the misfortune of implementing this exact item in C, Java, Python, and Go. And let me tell you, laying it out with CSP this way does make it simpler. Indeed, using CSP was far and away the cleanest one. If you focus on your inputs and outputs, you draw your connection diagrams, you make your pipelines, and you pay attention to your exit strategies, it should be easy for you too. Now, I'm going to leave you with some very practical advice for leaks, which caused us a ton of pain in our time in Go. You can mostly take these as items to watch for in code reviews. You need to stop your tickers. This is now in the documentation. It was not when we started. And MPEG has a ton of clocks, as I mentioned earlier. This is also a very small incremental leak, so it takes a long time to show up. And yes, that two weeks thing was actually something I got. In a similar note, if you're using a cancellation function on context, you need to call it. So when you're done with the context, you need to defer and cancel. This is also another one of those small incremental weeks that shows up in 2 weeks. And when you're doing TV, it's surprising how mad people get when it stops working one day. Speaking of which, don't defer inside of an infinite loop. This one is fantastically notable for being hard to find, and this will not show up on your profiler because it's part of the Go runtime. And that'll leave you wondering if GC is working. I think we spent 2 weeks at one point hunting down a bug that involved this. And yes, this mistake actually happens a lot because people are used to deferring. And just to reiterate, the runtime cannot collect a Go routine until it returns. Finish your Go routines. And with that, I'm finished as well. So, any questions before lunch?